Bill will, I'll do the introduction. The title of his presentation is The Revolution of Overhead Conductors and Why It Matters. Okay, let's see. Bill is, he's the Director of Business Development for the Northeastern US for CTC Global Corporation. He previously served as Senior Advisor for Climate Change to EPA Administrator Carol Browner. He holds a master's degree in public policy from Harvard University and a bachelor's degree in biology from the State University of New York at Buffalo, not far from here in Toronto. Okay, well, thank you very much. And Bill, if you'd take over, I will get out of the way. Let's see.
For having me today. Thanks, everyone. As Randy said, I'll be talking about overhead conductors today. I think for those of us who work on high voltage transmission, we've really never had the kind of attention that we're getting right now with you know, a lot of talk about infrastructure investments in the US. So there's really a moment here for all kinds of infrastructure, but a special moment, especially for high voltage transmission. So we're excited about that. And I think this is a good topic in light of that. So let me see if I can advance the slides. They're not advancing right now. Oh, there we go. So where did we begin with overhead conductors? Well, it started out with copper because it has such terrific conductivity. It's heavy and expensive. And in the early part of the 20th century, demand for copper for the First World War in the United States had forced the industry, the sort of relatively new electric industry to divert from copper to aluminum, which has the benefit of not being the most conductive. It's about 60% of the conductivity of copper. But what aluminum does have going for it is that it's the most conductive material by weight. So when you normalize by weight, aluminum is the best. So a series of aluminum conductors, and really the first one, there's a little bit out of order, but the first one and the one that really supported the industry for many, many years and still does is what's called aluminum conductor steel reinforced. And I will show you, if you can see in my tiny screen, that's this stuff here. The strands on the outside are aluminum and the strands in the middle are made out of steel. And the reason it's done that way is steel is stronger than aluminum. And so it also reduces the thermal sag of the conductor when it has a high current flowing through it. And so ACSR, aluminum conductor steel reinforced, has really been the industry standard for about a century now. Some variants of that were developed in subsequent years. I think it's about 40 plus years ago now. ACSS was supported, again, higher thermal limits so it can run at a higher temperature for higher capacity in the same corridor. The overall strength is a bit less, but and it still has some sag issues, but again, developed really to add capacity by raising the operating temperature. And then there's some other technologies that have been added in over the years. The high strength steel was added to ACSS, again, to reduce some of the sag issues. This novel conductor used very rarely in the US, but used overseas some, called GAP, which inserts a layer of sort of a oil grease-like substance in between the core and the conductive strands on the outside. That is being phased out these days because the grease can drip down and create other issues like noise and corona. So that's kind of being phased out. It had some benefits in terms of sag. Another in-bar core, a slightly different core, has a lower coefficient of thermal expansion, again, has some other issues that are making it less desirable. And then another composite core, which is a ceramic metal composite in the core, again, to try to get some extra strength and some reduction in thermal sag, but has some other limitations as well. And that brings us to the product I'm going to focus on for this discussion. But you can see really the issue here, and as this conversation that we're having today about investing in transmission proceeds, one of the issues is how do we make our transmission system and our network more robust? How do we add capacity to it when we know that nobody likes to look at big transmission lines, nobody wants to give up additional land for new transmission corridors? So how do we get the most out of the corridors that we have, out of the network that we have, to accommodate, changing generation resources from a principally fossil generated fleet of generation to one that's dependent on renewable resources that are located in different places? And then how do we also accommodate at the same time a big increase in demand for electricity as we electrify, end uses like transportation and many other end uses moving to electricity? So with that, we'll talk about what's called C Conductor, which is both a industry classification and a registered trademark of CTC Global. And C stands for aluminum conductor composite core. In this case, the composite is a carbon fiber composite core. And so instead of the steel core I showed you here, which is not in great focus, I'll bring it up here. This is what C looks like. You can see better the picture there. This core is a carbon fiber composite. It's much more thermally stable than steel. It's much stronger and lighter. It resists corrosion and fatigue. It meets industry standards. So it has the lowest thermal sag. And the big advantage of this is that it can run at high temperature with the same weight and the same diameter without having a clearance violation. That is something that would cause it to hit anything on the ground or vegetation underneath the line, the kinds of things that can short out the lines and interrupt electric service, but also can do things like start fires. We've seen a lot of that out in the Western United States. It's about double the capacity for the same diameter wire of the ACSR, the long-time industry standard. And it's the most energy efficient wire. So for the same diameter, you get about 28% more aluminum on the wire. And that means that at every ampacity, every amount of amps running through the wire, the resistance is lower and the line losses are about 30% lower at every ampacity, every temperature. It's running at a lower temperature. I'll get into that in a second. So, and that obviously, just like an LED light bulb or something like that, it's, less waste means more energy efficiency. It saves money. It saves the greenhouse gas emissions associated with generating power. It requires less power generation capacity to meet the demand, the electric load on the other side of the line. So this is just an illustration of how revolutionary adding the carbon fiber composite material to the core of the conductor is. You can see the relationship here. This is the industry standard, and this looks at the capacity of the line on the horizontal axis and the efficiency of the line on the vertical axis. And you can see that that some of the products that have been introduced over the years have achieved better performance on one or both of these metrics over the years, but that really ACCC stands out as being sort of an outlier. And again, that has to do with the material that's being used in the core of the wire. And just to put a finer point on this, this is a comparison looking at the thermal sag on the vertical axis, the temperature of the wire across the horizontal axis, comparing a bunch of conductors. This was done many years ago. And so what happened, what was done here was the conductor was, all of the conductors were the same size, the Drake size. The bird names are used for conductor sizes. So they all had the same diameter. And this was a 65-meter span. All of the conductors were run. The endpoint represents 1,600 amps being run through the conductor for each one. And as you can see here, you know, every transmission line has a clearance requirement. That is, the wire cannot fall below a certain level in order to maintain the required clearance from the ground or from anything that's underneath the line. And in this case, it was set here just around 40 inches for this test in a laboratory. But you can see here the big takeaways are that all of these conductors, and GAP is an exception, and we explain why that's out, but the blue triangles are ACCC, and all of these other conductors, ACSR and ACSS being the most widely used, are basically made out of metal. And they achieve a very high ampacity by running at very, very high temperatures, over 200, well over 200 degrees Celsius, in most cases, over 240 degrees Celsius. And so they have to run very hot to get to the ampacity. But they're also, as they run at those high temperatures, you can see that the sag, you know, exceeds the limit set in this test. ACCC reaches because carbon fiber is so thermally stable, ACCC hits what we call a thermal knee point, somewhere between about 60 and 80 degrees Celsius. And then there's virtually no additional sag after that, even when it's run up to its maximum operating temperature of 180 degrees Celsius. And you can see that, you know, really important point for efficiency here is that because the ACCC achieves the ampacity at such a low temperature relative to the other wires, that's where the energy savings come from, right? The hotter something is, the more energy it's wasting in the case of conductors. And you can see that the difference here is somewhere between, you know, it's around 50 to 70 degrees Celsius. So it's quite a large difference and quite a large savings. Hopefully that's clear. I know this is a very, very busy chart. Thanks for bearing with me on that. So what this allows ACCC to do is I'm using ACCC interchangeably here with all carbon fiber core conductors. There are several other companies that produce these on the market globally, and the number of market entrants is growing by the day. So we may have been the first ones to produce this product at CTC Global. We may have invented this technology, but the technology is out there and it's being picked up by a lot of companies out there today. And I expect there'll be many, many more in coming years. So what does this allow utilities and transmission owning companies to do? It lets them increase the capacity in their existing corridors by retaining existing towers, so-called reconductor projects. So they simply change out the wire and they can keep the same structures, meet all the clearances, and add a lot of capacity and improve their efficiency. When the condition of the structures, as is often the case, we have an old system in North America, has deteriorated to the point where they must be replaced, it can allow the utility to replace, to add capacity without increasing the size of the structures that were there to start with. So that's important because the width of the right-of-way is directly proportional to the height of the towers in the corridor. So if a utility has an existing right-of-way, even if the structures are deteriorated and they want to add capacity and efficiency, or they need to meet new requirements for storm hardening, they can do that with towers that are the same size as the ones that they're replacing. And that obviates the need to acquire new right-of-way, and it obviates the need for them to spend the extra money to make larger structures. And it also, there are visual impacts or all sorts of other considerations when, they go for, say, an 80-foot tower to a 100-foot tower. That, is a really, really big impact in terms of visual impacts, in terms of acquiring right-of-way and so forth. It's very expensive. Same thing goes for new lines. Again, reduce the upfront capital costs. You can have longer spans, you can get the same capacity, you can get more capacity in the same space. Again, the other examples, long span applications, reduced sag allows ACCC to get across things like rivers and in marine environments and estuaries where you have to put structures in the water, that you'll have fewer structures, you'll be able to do it in a more efficient manner. And corrosive environments, the carbon fiber composite contacting the aluminum, it really doesn't allow for corrosion. There's no real corrosive surface available there, so highly resistant to corrosion. So why carbon fiber? Carbon fiber is a material right now that's really replacing metal, replacing steel and aluminum and other metals in a very, very wide variety of applications across the economy and in defense and many, many other industries. Our inventors at CTC Global were people who came out of the aerospace industry, was the industry that really pioneered a lot of carbon fiber composite applications. So our inventors came out of that industry and were looking for new applications for carbon fiber composites and came up with the idea to use it as a core material in overhead electrical conductors. And that's how we got started. Today, new passenger airplanes, new airplanes are made of, more than 50% composite materials. And that's up from about 10 to 20% just 20 years ago. Cars are headed in the same direction. It's nowadays, I think it's there are so many things that we have today that are made with some amount or entirely of carbon composites that it's just become commonplace. And again, the reason being that it's light, it's strong, but the most important reason for it's light and strong. The two big reasons it's so successful in this application in overhead conductors, two I think that I'd like to spend some time on, are thermal stability, which I already talked about a little bit, and also this ability to resist cyclic load fatigue. That is the like in an airplane where wings and other parts of the airplane are constantly subjected to vibration and forces over and over again. The same thing happens with overhead conductors. They're blown in the wind and stretched. They accumulate ice and they sag. And obviously they're heated and cooled constantly, many, many cycles every day, and they're in service for decades. So this ability to metal, when subjected to those kinds of forces, eventually experiences fatigue and plastic deformation. And in the case of overhead conductors, what we see is something called a permanent sag condition. So it doesn't bounce back to its original form. In the case of carbon fiber composites, they're extremely good at bouncing back. And they're very elastic and they resist this plastic deformation over time, better than really any other material that's out there. So that's one of the reasons why they're so widely used and why the material is so desirable. We've done a lot of testing. This is a partial list of the kinds of testing that's been done since ACCC was introduced in 2003 and first commercial installation in 2005. So anybody interested in learning more about all of the kinds of testing that has been done for this material in the field and in the projects that are already installed. We're happy to talk about that and provide you with whatever information you need. But this is, we have literally hundreds of different tests and reports, industry standards and beyond, to share with folks who are interested. I'm just going to cover a couple of examples to illustrate, how this works in the lab and in the field. This is a test that was conducted, again, illustrative of a very rigorous, intense lab test to show, and again, to try to accelerate, it's called a accelerated aging test, and subjected to 100 million cycles of vibration and 100,000 cycles of galloping. That's where the wire is going like this. You can see how resistant the ACCC is, partly due to the trapezoidal shape of the wires, but also due to the strength of the material and its resistance to cyclic load fatigue. And you can see that over time, the conventional conductors are going to have fatigue failure. And even if they don't have this kind of failure in the field strictly from the application of these forces, it's very uncommon to see that. But what is much more common is that these tiny fractures allow corrosion to start. And corrosion is actually the most common reason that conductors fail in the field. So this is just an illustration of how that the design of the materials prevent that from happening. This was an actual installation in Oklahoma of our wire. An EF5 tornado came through the region, and in the towers that are holding up this, in one of the towers that are holding up this line, an oil tank was thrown into the structure, and the structure buckled as a result, and the shock wave from that was enough to break the aluminum strands on the conductor, but the core was so strong that it actually held up the structure and allowed the crews to come in to support the structure and make a fast repair in just a few hours and get the line back in service, which was really important. If the structure, if this wire had actually snapped, as would have likely happened with the steel core wire, we would have had sort of a catastrophic cascading failure that would have taken several days to put back into service. And so it was very important, especially in a region that had just been hit by a tornado, to get the electric power back in service. So that's just an example of the resiliency and reliability that you get from using this type of material. This is another case in Nevada where a wildfire came through and there were wooden structures. You can see the remnants of them. It burned them down, and the wire and the insulators and the cross arm on the structure fell to the ground. The conductor, our conductor ACCC, was not damaged. In fact, they were able to come in, put new structures in, lift it up with helicopters, replace the damaged cross arms and insulators, and without replacing the wire, get the line back in service. This is a project, a very large project that illustrates a lot of the benefits of this wire that was completed by American Electric Power in the Corpus Christi area of Texas. American Electric Power was given a very, very difficult request from the grid operators in Texas and the regulators. They said, okay, here's what you have to do for a very high voltage line, a 345 kV line, double circuit line, 240 circuit miles. You have to replace this, you have to upgrade this line. You have to, just about double the capacity. You have to, you can't replace the structures because the corridor is very limited. And you can't take the line out of service. You have to keep it in service. So they ended up choosing ACCC for the project, and along with some other innovative technologies, were able to complete what is still the largest energized reconductoring project ever completed in the world. And it really was complete. It was completed ahead of schedule. It was completed under budget, and then it added these line loss savings, which are staggering, about $15 million a year. So the first year savings in line losses actually not only paid for the incremental cost of the conductor, they paid for all of the conductor. So the conductor was essentially free. And it ended up winning the Edison Electric Institute Transmission Project of the Year in 2016. Let's see. This is another one close to where I live in Massachusetts. National Grid needed to reconductor this much smaller project, some existing 115 kilovolt lines to increase ampacity and meet modern clearance and safety requirements. The interesting part here is this is in southeastern Massachusetts, in a very old part of the electric grid. They wanted to avoid replacing 95-year-old steel lattice towers. They inspected the structures and the foundations, and they found that they were actually very well maintained and were in good condition. They also needed to increase the ampacity and meet modern clearance requirements. So they needed better clearance than they already had while they increased the ampacity and avoid replacing the structures. And again, thanks to the carbon fiber composite conductor, they were able to do that. They added in technology that's from a Canadian company, Amjack, that actually added a few feet to several of the structures. What they do is they cut out a section of the structure, and while it's in place, they can jack it up and insert a few feet of structure and then put it back together. And they were able to do that. And they used some micropiles to strengthen the foundations to accommodate, have a foundation would accommodate the slightly taller structures. Even with all of that, it ended up saving, the project was about $4 million less in cost, $3 to $4 million, faster schedule, safe process, and reduced environmental impacts. Just for the extreme conditions that can be addressed with ACCC, this is a project here that is a very heavy ice solution in Scotland. This area experiences extreme ice of about a 2.4 inch radial ice. Just for comparison, the typical maximum ice we see in most of North America, except in a few parts of Canada, is about 1.5 inches. So 2.4 inches is extremely high ice loading. They're now exclusively using ACCC Monte Carlo in this application, and it also won an award, this project. You can see in the picture on the left-hand side the difference in sag on the two wires. This is thermal sag, but you can see on the left is where the ACCC has been installed, and on the right is where the traditional conventional ACSR conductor is still in there. So you can see how dramatically different the sag is on those two wires. This picture right here. So just to talk a little bit more about the enormous benefits that this technology can bring more broadly, not just in terms of providing an engineering solution, but just in terms of saving energy and saving capacity. We looked at a project in New York that's designed to bring clean energy in and move it around New York State and downstate. There's several projects that New York is working on. This is one of them. And in this case, you can see the incremental cost of the wire replacing the conventional wire with the carbon fiber core wire was about $7 million for this project, about 7.4 million. The benefits, the simple benefits we could calculate in a straightforward fashion, and this is a very conservative estimate, were about $88 million. So looking at net benefits of 80 million over the life of the project and a benefit cost ratio about 12 to 1. So even if we just looked at the direct line loss savings, which are a simple electrical resistance calculation, we're talking about a benefit cost ratio of around 10 to 1, again, on a total project cost of $440 million. So, these benefits can be extremely large. As you can see, in this project, the ACCC was a lot stronger, almost twice as strong as the conductor that is being proposed. The ampacity is higher at the continuous temperature, so it's providing more transfer capacity. And it's actually the ACCC, despite having a lot more aluminum in the wire, about 28% more, it's actually lighter in weight, and that's because the core material is so much lighter. You can see the sag at the maximum temperature, again, to achieve clearances is dramatically lower for ACCC. That it sags only to about 43 feet versus about 59 feet. So that's a 16-foot difference. And even under extreme ice, the ACCC conductor is slightly better than the ACSS wire. So from engineering performance, it's better. Every aspect it's better, and it saves a lot of money and provides a lot of benefits. So again, this is just a story of a new technology that has some fundamentally different physical characteristics, and provides a big leap in performance for the whole grid. We've even seen internationally that in some utilities outside of the United States, we're seeing projects that are already counting the carbon reduction benefits that are associated with the efficiency that is delivered by a carbon fiber composite conductor. The Asian Development Bank has recognized them in several transmission projects in Bangladesh. This is just a quote from their report on this. Significant amounts of carbon reductions. The project was actually awarded an additional grant of about $7 million that was directly related to the carbon savings. So they paid a price for the carbon, the estimated carbon savings over the life of the project, and that money went to the project. We estimate that in the 900 plus projects around the world currently using ACCC, that about 3 million metric tons of carbon per year are being saved, equivalent of moving about 750,000 cars from the road. And that number is growing. Utilities are committing to carbon reductions, so about 71% of American utility customers are served by a company with a carbon emissions reduction goal. 73 utilities have publicly stated carbon goals. 51 of those have goals of carbon-free or net zero emissions by 2050. So we think it's just a matter of time before those same kinds of metrics are going to be applied to transmission investments in the United States. We already see it in several countries overseas, but we think it's coming very quickly here to the US in one form or another. One example, again, close to home for me, is National Grid, which operates a lot of the grid in Massachusetts, is committed to a 45% reduction in greenhouse gas emissions by 2020 and net zero carbon emissions by 2050. We're also seeing at the federal level, how am I doing on time there, Randy? Good? Okay. I can't hear you. Sorry. I think you're on mute.
My apologies. Everything is fine. As long as the people are still in the meeting and they're actively watching, then I don't interfere.
Okay, great. I didn't.
So keep going.
I'll keep going. Anyway, so there are policy changes afoot. I mean, I think we're all aware there's a big infrastructure bill in the United States. And I think, as others have mentioned in prior presentations, it's something that's influencing the transmission industry, as it is a lot of us across the entire infrastructure business very broadly. I'll just provide a couple of examples. A notable one, last year, the Federal Energy Regulatory Commission in the United States introduced the idea of using a benefits framework to evaluate investments in utility infrastructure, transmission in particular. There has been a historic emphasis only on costs and not on benefits. And so they're trying to move to a more balanced approach, as FERC Chairman Rich Glick said, to wisely use customers' money. And we're very supportive of that idea of shifting away from what we see as sort of an undue emphasis on first costs and toward a more balanced evaluation of benefits costs. Products like ours and other products that provide efficiency gains, if they're slightly more expensive, they can be really excluded from consideration, even if they increase project costs by just a few percent. So we're trying to see if and we see there's some flexibility for saying, let's not make, penny wise, pound foolish decisions going forward that aren't in the interest of electric consumers and businesses and the economy as a whole. Our carbon reductions and efficiency have been certified by third parties. I think we're the only overhead conductor that has that certification. This is just to give you an idea of, how much is out there, how widely used is our product. As I said, our first commercial installation took place in 2005. It's still up there. It's in Niagara Falls, New York, Randy, and just down the road. And it's a few mile test line, but it's still there. Anybody, it's owned by Niagara Mohawk National, part of National Grid. So you can see we've got about 900 projects worldwide. Our biggest volume is in Asia right now. A lot of that has to do with the fact that a lot of countries who are really adding to their grids significantly now to improve electric service and extend electric service are finding our product to be very capital efficient means of doing that. So, we do a tremendous amount of business in Asia, but also really around the world. It's pretty balanced and lots also even in North America, and we expect that to grow a lot in the coming years. There's a number of different sort of flavors of ACCC conductor. Our ULS product and AZR are designed to deal with heavy ice loads. So the ULS uses a stiffer carbon fiber and it has a higher ratio of carbon to glass fibers in the core, in the composite, and that makes it stronger and resists ice loading. So in places where ice loading is an issue, it's a really effective product. AZR does a similar thing. It uses a zirconium alloy in the aluminum to increase the strength of the wire and again resist ice loading. And they can also be combined for extreme conditions. The way our product is produced, we make the core at CTC Global, and the finished conductor is produced under a license agreement with our partners around the world. We've got around 30 global partners, the largest conductor manufacturers in the world. That's basically how they produce all conductors. So the producers of overhead wire are companies that strand aluminum. What they generally do is they purchase the core material from somebody else. If it's a steel core wire, they purchase the steel core and then they put the aluminum on it. In our case, they purchase the carbon fiber composite from us, and they put the aluminum on it and ship it to the customer. That's proven to be a very efficient, cost-effective, and gives us very competitive pricing in the market. The hardware that our conductor uses is simple and is produced by all the major, most of the major hardware manufacturers around the world. Again, this gives us an ability to provide multiple bids in any market per utility procurement rules. And again, illustrating this really just to let folks know that the technology is out there. It's very widely used in the industry. it's new in the sense that it's not, the technology that's been in use for 100 years, but it is very well established.
Okay. All right. We have some questions.
Sure. Great.
How close are you to the end here?
I'm right at the end. I can jump over this for now, and
okay,
we can handle the questions.
Let's talk, because there's quite a few comments and suggestions here I wanted to cover with you.
Please do. Yeah.
Okay, let's see. Okay, Jody mentioned the presentation is quite timely. We're thinking about changing our standard from copper to ACSR. And Dennis asks us, he mentions, with the higher operating temperatures, if used with polymer insulators, are there special requirements for high temperature hardware and insulation?
Great question. So all the hardware, ACCC hardware that's provided by the major hardware manufacturers is rated for our operating and emergency temperatures, 180 and 200. Polymer insulators have been used with ACCC. The SEMA project that I just mentioned, the one in National Grid, did use polymer insulators. So we haven't experienced any problems with that. We have a lot of projects that use the hardware and the insulators. So really nothing different than what we've seen with other wires. Again, ACSS, which is the high temperature variant of ACSR, operates at a much higher temperature than ACCC. And again, those same insulators are used. So the procedures are all industry standard, very easy to master, very slight differences from standard insulation techniques.
Okay, next question was, I'm curious about this is from Jody. I'm curious about the ability to bend for installations.
Great question. So there are some bending limitations on ACCC, but they don't require any non-standard equipment. There might be a few wheels here and there that would be a little larger than you would use for another wire, but they're all equipment that are stocked by every transmission construction firm out there. So it's just a matter. We provide very, very detailed guidance on the bending limits, and we provide free training with every installation, and we have one of our certified master installers on every site. Again, the changes are very small, but they're important, and we want to make sure everybody understands them. We provide detailed equipment lists with every installation as well. So we really don't leave anything to chance. Again, the differences are small, but we've decided to really invest heavily in this over many, many years. And now we have really, we would say, the most comprehensive installation support of any product in the industry. And again, 900 plus projects, including, you see the picture on the screen now. This is a large project in Malaysia. We have many, many dramatic installations like this that have been successful. We've done everything from 800 kV DC in South Korea to 12 kV lines. So,
all right,
good question.
Okay, we have another long question and comment. The ACCC wire form looks very similar to another power distribution conductor, Newell. Understanding that Newell is not a transmission line, is there similarities in the metallurgy of the materials? If not, is there a move to go towards that type of current carrying capacity with the carbon fiber core? And when will we be able to look forward to this being in the Canadian and Ontario electrical code books with its appropriate CSA type designation and its trade designation?
Okay, so those are good questions. I'll have to, if someone could submit to me the specifics of the other product, which I don't know,
okay,
I'd be happy to talk about
all
that.
right.
But what I will say is that,
yeah.
Again, that there is no metal in the core of ACCC. Obviously, it's a carbon fiber composite. There's no metal in it at all. And the metal we use is fully annealed 1350O aluminum. which is the most conductive aluminum that you can put on any wire.
Mm-hmm.
So we again, because of the properties of our core, we can use the softest, most conductive aluminum that exists. And that's what we use to maximize the conductivity. But I'd be happy to follow up. We are industry standard ASTM, IEEE. We've met everything out there. We're sold in 65 countries
Mm-hmm.
now around the world. So
okay.
if there's any standard that we're not showing up in, I certainly want to know about that, and my colleagues would too. So we're happy to follow up with anybody to answer any more detailed questions on that.